Now that we're working with a graph data structure, we need a way that we can traverse all elements of the graph. We had a way to traverse items if we were working with a list or vector or any other container we've seen so far. With a linear structure, with a vector, array, a list, we could just start at the beginning and work our way to one by one to the end of our container. Or if we had a tree, since this was hierarchical, we saw a pre-order or post-order traversal, level order traversal in your homework. And for binary trees, we also had an in-order traversal. So we're going to define two different ways that we can traverse a graph. So we'll see depth first search, or DFS for short, and in the next video, breadth first search, or BFS for short. So both of them will give us a way that we can traverse every object of our graph. So we'll visit each edge and each vertex exactly once. Now, as a result of these traversals, we will obtain what's called a spanning forest. So before we get into what depth first search is, how it works, let me give you a few definitions that we'll need in order to understand what it's actually doing, and then we'll see how it can be used and what other applications it has. So we say that a subgraph S of a given graph is itself a graph, so that we pick just a subset of vertices and a subset of edges. So if we pick a particular edge to include in our graph, then we also include the endpoints, the end vertices of that edge. So for example, let's say we're given the following graph with all vertices and edges. A subgraph of this one would be if we were to choose this edge and this edge and this one. So what we have in red here is an example of a subgraph. We could also choose, let's say, for the following graph, another subgraph would be maybe we take this edge and these vertices. So this is just, we pick a subset of vertices and a subset of edges. If we take an edge, we include the endpoints of that edge as well. And this gives us a subgraph. So this is just a portion of our original graph. Now we say that a subgraph is spanning if it contains all of the vertices of our original graph. So suppose we had this graph. A spanning subgraph would be one where we include each of these edges, and then we include only a subset of edges. So maybe we include this edge, this one, and this one. Or to give you another example, maybe we have given this graph. Oops, this is OneNote. Given this graph, a spanning subgraph would be where we include all vertices. So this is spanning in the sense that it includes all vertices. And we choose only a subset of edges. Maybe we don't choose any edges, or maybe we choose these edges. So this would be an example of a spanning subgraph. Okay, next we have to define how a graph would be connected. So we say a graph is connected if between every pair of vertices there's a path that connects them. So this is an example of a connected graph. If we pick this vertex and this vertex, we have at least one path that connects them. Between this vertex and this vertex, we have at least one path that connects them. So between every possible pair, we have a connecting path. Now our graph might not be connected, but we can at least break it down into connected components. So we have here one graph. This entire thing is one graph, which consists of two connected components. Here we have one connected component, and this is our second connected component. So this is a maximal connected subgraph of our original graph. So we can't possibly add to this any more vertices or edges and still keep that this subgraph is connected. Now our original graph is connected if and only if it has exactly one connected component. If it has more than one connected component, then that means it's not a connected graph. Okay, one more thing which we'll need are trees and forests. Now you've seen trees before from the perspective of a rooted tree, where we have a distinguished root vertex, and then every vertex has a parent and some number of children. But we're going to define a tree a little bit differently here, a little bit more generically, which is a free tree. So we don't have any fixed vertex, which is the root. This is just an undirected graph, which is connected, which means every pair of vertices has a path between them. Every vertex has a way to get to every other vertex. And it has no cycles. Now, keeping with the arboreal definitions or terms here, we say that a forest, so this entire thing is one forest, is an undirected graph which has no cycles. So we just get rid of the restriction that it has to be connected. It just has no cycles. So a forest consists of subgraphs, where each connected component is a subgraph, which is a tree. Okay, so now a spanning tree or spanning forest, this would be, in the case of a spanning tree, a connected graph which is spanning in the sense that it includes every vertex of our original graph, but it's also a tree. That means that we have here in bold all of those edges which we're including and the endpoints. So we've included all vertices of our original graph. We didn't include some of these edges. We included just enough edges in order to connect every vertex, so that every vertex has a way, some path in order to get to every other vertex, but not enough edges to where we would create a cycle. So this would be some path which starts and ends at the same vertex. So we create a spanning tree. These aren't unique unless our original graph was a tree. So for example, I could take from this graph a different spanning tree where I include, let's say, this edge and its endpoints, this edge and its endpoints, this edge and its endpoints, and this one. So this is also an example of a spanning tree, as is this one. And then a spanning forest would just be a spanning subgraph that is a forest. So we have a spanning subgraph which is has no cycles. Might not be connected, but it has no cycles and it includes every vertex of our original graph. Now, since a tree has no cycles, then the number of edges in that spanning tree, not in our original graph, is big O of n. It's exactly n minus 1. So this is really the least number of edges for a tree. This is the least number of edges we'd have to add or include in order to keep that our graph is connected. Spanning trees are useful because they can connect all vertices of a graph, but do so in such a way which minimizes the number of edges that are necessary to keep the graph still connected, which has many applications in designing communication networks so that all nodes can communicate, but it uses the least amount of connections to set up. Similarly, it can be used for designing road networks, telephone networks, for laying down coaxial cable to provide internet access, or applied to an electrical grid, etc. So depth-first search, as a result, will give us a spanning forest of our graph. Specifically, it'll give us one spanning tree for each connected component of the graph.